Today, I'm going to talk about randomness. We ask and partially answer the question, is untrusted randomness helpful? I'm Zhan, and this is a joint work with Girish and Randomness. So normally in a randomized algorithm, we have an input X of n bits, and the algorithm has access to random bits that are independently and uniformly drawn from 0 and 1. In the case of a space-bounded algorithm, these random bits came in as a string. And the algorithm generates an output that can be seen as a function, depends on the input and the random bits. And for today's talk, we only care about decision problems, so we assume that the output is either 0 or 1. Now, a priori, a randomized algorithm can use as many as the time limit number of random bits, but in reality, truly random bits are very rare, and the people address this issue by taking notions of like pseudo-randomness or weak random sources. However, today, we are going to talk about a very strong notion of bad randomness in the sense that these random bits are untrusted, that they can be adversarially or even maliciously chosen, even upon seeing the input X. Of course, just as it is, this model is not so interesting because if these random bits can be adversarially chosen, then we just choose them to be all zeros, and the algorithm is just as strong as a deterministic algorithm, right? So we want the algorithm to have some kind of ways to verify these random bits, that they can check these random bits are truly random. So let's say we have a prover and a verifier that are both efficient, and initially they are both given access to an input X. Now the prover also has access to unlimited number of random bits, which to the verifier, they are untrusted because they can be manipulated by the prover. The prover and the verifier interact with each other, and eventually the prover needs to send the verifier a proof that you can think of it as a proof for randomness. And the verifier needs to either accept the proof and output an answer being either 0 or 1, or it detects something fishy in the proof and chooses to abort and outputs a perpendicular symbol that represents I don't know. Now, if the verifier is deterministic and we want the verifier to never be fooled by a dishonest prover, then you can see that this model is exactly the zero-error probabilistic model. So to make things more interesting, we also allow the verifier to have its own randomness that are trusted and truly random, but only for a limited number of random bits. Now we define this complexity class RPP, which represents robustly probabilistic polynomial time, with a parameter k. And we say a language is in RPPK if there exists polynomial time prover and polynomial time verifier, such that for every input, this protocol outputs the correct answer with a high probability, while for any computationally unbounded and probably dishonest prover, P prime, this protocol outputs either the correct answer or I don't know with high probability. And of course, the verifier could only use order of k truly trusted random bits. Now let's come back to the viewpoint of a randomized algorithm. We can show that the above interactive proof model is equivalent to a randomized algorithm that has access to two parts of random bits, where one part contains untrusted random bits that can be adversarially chosen, and another part contains trusted random bits that are always truly random, but only has a limited number of bits. And the algorithm, besides outputting 0 or 1, it is also allowed to output I don't know. Now, a language is in this robustly probabilistic polynomial time with parameter k. If there exists a polynomial time randomized algorithm with order of k trusted random bits, such that for every input, if the untrusted random bits are indeed truly random, the algorithm outputs the correct answer with high probability, while for every fixed value of the untrusted random bits, the algorithm outputs either the correct answer or I don't know with high probability. And this probability is only over the randomness of the trusted random bits. So where does this class RPPK stand? So let's first think of the case when there are no untrusted random bits. And if the number of trusted random bits is unbounded, then it corresponds to the class of BPP, the bounded error probabilistic polynomial time. And if the number of trusted random bits is limited to order of k, then we denote this class by BPP with parameter k. And when k goes down to logarithmic of the input size, it can be fully randomized. So it is equivalent to having 0 random bits, and the class is just deterministic polynomial time p. Now, with unlimited number of untrusted random bits, we denote this class by RPPK. And we say that when k goes down to 0, it is basically 0 error probabilistic. So it's collapsed to ZPP. And actually, it is still in ZPP when k is only logarithmic in n. So we have RPP log n is still equals to ZPP. On the other side, when you have unlimited number of trusted random bits, the class is still containing BPP. And from the definition, RPPK clearly contains BPPK. And we can show that it actually contains BPPK with ZPP oracles. Now, to answer the question, is untrusted randomness helpful? It is only helpful when this containment is strict. But with common belief, everything in this diagram should collapse to P. So we don't actually know if it is helpful or not. But there is indeed a conditional separation that if BPPK and ZPP do not contain one another, then RPPK is indeed a strictly bigger class than both BPPK and ZPP. Now, things are more interesting when you consider log-space robustly randomized algorithms. We can similarly define the class RPLK, that stands for robustly random probabilistic log space. And the language is in RPLK if there exists a log space algorithm with order of k trusted random bits, such that the same thing holds that for every x, if the untrusted random bits is truly random, it outputs the correct answer with high probability, while for every adversarially fixed untrusted random bits, the probability of it outputting either the correct answer or I don't know is high. Now, this class also has equivalent formulation in the form of interactive proofs, although here the proof protocols are not really interactive anymore. We have that a language is in RPLK if and only if there exists a log space prover that upon the input x produce a proof pi x of polynomial length, and the log space verifier with order of k random bits that reads the proof as a one-pass string, so that with the honest proof, it gets the correct output with high probability, while for every possible proof, the verifier either outputs the correct answer or outputs I don't know with high probability. Now, what we know about log-space probabilistic computation is that the best known pseudorandom generators have C-length log square n. So we know that bounded error probabilistic log space can only use log square n truly random bits. and whether or not it can be reduced to log n so that it can be fully randomized is a very big open problem. What we show in this work is that with the help of untrusted random bits, you can actually reduce the number of trusted random bits to log n. So in the form of this complexity classes, we have BPL equals to RPL with log n truly random bits. And in this sense, for our current knowledge, it means that untrusted random bits is indeed helpful for log-space computation. And here we are going to sketch a proof for this result by designing a log-space streaming proof for every language in BPL. So for every language in BPL, there's a log-space algorithm that solves it. And with every input x, this algorithm can be represented by a stochastic matrix mx that has entries either 0, 1, or 1/2 that represents the transition matrix between the memory states in each step. So the dimension of the matrix is m, which represents the number of possible memory states, which is polynomial in n. This matrix has the property that first, it is uniformly computable from x in log space. And if we assume that the initial state of the algorithm is state 1, then the probability of reaching state I at time t is exactly the entry in the ith row and the first column in the matrix that is the t times power of mx. And if we assume that there is only one accepting state, which is the state m, then the probability of the algorithm accepts is the entry in the mth row and the first column in the matrix that is the big T time power of mx, where big T is the time of the algorithm, which is polynomial in n. Now, what the prover does is that for every time t and every state I, it outputs a number that approximates this matrix entry, that is the probability of reaching state I at time t. And it can approximate this number up to polynomially small error just by simulating the log space algorithm for polynomially number of times. And we think of its output as a string that contains big T number of vectors, where each vector approximates a distribution. What the verifier does is that it needs to check whether these vectors that approximate distribution is indeed the distribution of the original algorithm that reaches these states in different time steps. So what it checks is that whether for every time t, the difference between the vector vt and the product of the transition matrix mt with vt minus 1 is small. And it checks this by computing the following value d. So this d value looks complicated, but to parse it, first we know that there's a coefficient alpha for every time t and state I. These alpha ti are four-wise independent random variables taking values in -1 or 1, and each one of them has mean 0. So they can be generated from seeds of length logarithmic in n, and each one of them can be computed from the seeds in log space. And the value in the parentheses is basically just the entries of these difference vectors that we want to show that are small. And if you look at if you change the form of the formulation of D and look at the coefficient between each VTI, the coefficient each one of them can be computed in log space. So the D value can be computed by just taking a stream of VTI in log space. And we can show that if the difference vector has small L1 norm, say smaller than delta for every t, then with high probability, this d value is smaller than some threshold, say 30 times delta times t. And the verifier also knows the correct answer by just looking at the last number that the prover outputs, the V big T of state M, because this number is very close to the actual accept probability of the original Logspace algorithm. While on the other hand, if the difference between the final value that the prover outputs with the actual accept probability is high, say it's larger than 1/4, then by choosing delta to be a small enough number, but still polynomial in N, we can show that with high probability, this d value is larger than the threshold of 30 times delta times t. And so what the verifier actually does is first to compute this d value and checks that if it is larger than the threshold or smaller. If it is larger than the threshold, it means that the proof is not really correct and it aborts. While if it is smaller than the threshold, it can safely decide the output just by looking at whether the last probability value is larger than 1/2 or smaller than 1/2. In which case, with high probability, it is the correct answer. So to conclude, we propose two hierarchies of robustly probabilistic classes that uses untrusted random bits, and they are robust in the sense that when the untrusted random bits are adversarially chosen, it still does not give the wrong output with high probability. So for polynomial time, this class RPLK using K trusted random bits is sandwiched between BPP and ZPP. And when K goes down to log N, it equals to ZPP. So K ranges from polynomial to log N. While for logarithmic space, this class RPLK is sandwiched between BPL and ZPL. And something I didn't mention is that when K is equal to 0, it is basically a zero error probabilistic log space. So it's ZPL, but it's still in ZPL even when K is constant. So for log space, K ranges between log N and the constant. With the common belief that BPP equals to P and BPL equals to L, both hierarchies collapse. So showing any of these inclusion being equality is an intriguing intermediate open problem towards proving the whole thing that BPP equals to ZPP or BPL equals to ZPL. But we still don't know if the untrusted random bits are helpful in the case of polynomial time. We kind of know it's helpful for log space, but it might be just because of our lack of knowledge for de-randomizing log space computation. But in the query model, we can show that there are indeed unconditional separations between robustly randomized algorithms and bounded error probabilistic algorithms or zero error probabilistic algorithms. So in the last slides, let me state the result for these separations. We show that there is a promise problem with input of size 2 to the n plus k for every n and k, such that first it can be solved by a robustly randomized algorithm using k trusted random bits and n untrusted random bits with only one query to the input. On the other hand, any bounded error randomized algorithm using less than n trusted random bits requires exponential in n number of queries. Also, for any zero error randomized algorithm with however many random bits it uses, it requires exponential in k number of queries. So taking k, for example, to be log n, we show that in this case, untrusted randomness is unconditionally helpful in the query model. And that's all for this time. Thank you.